All right, we're ready for a brand new chapter, chapter 9. The good news is it's another chi-square chapter, very similar to what we've been doing before. It's the chi-square contingency test. And so contingency, just the definition of the word, refers to like dependence on something like, I'll give you my car contingent on you paying me $10,000 or whatever. So contingent is the notion of dependence. So this is really a test of independence between a couple of different variables. So, for instance, imagine that you want to know whether the effects of watering some pine trees depend on the microhabitat in which the pines were grown. So the null hypothesis, once again, we want the null to be specific, might be that watering is independent of the habitat type, and the alternative is just that it's not that, so it's in some way dependent. So Jorge Castro in this 2006 paper, there's a link here on the slides, looks at the emergence of seedlings on watered and unwatered conditions in 3 different microhabitats. The paper looks at several other things, but this is just one table that we can extract from that data. Okay, so we've got essentially 2 variables here. We have watered or unwatered, that's a binary variable, and then we've got a habitat variable that can be either open or some kind of spiny shrub or a juniper-based habitat. So there's another categorical variable that has 3 categories. The null hypothesis that we might be interested in testing is whether the effect of watering is independent of the habitat type. So this table here is called a contingency table. It depicts the association or the potential association between 2 different variables. There's a variable along the x-axis and there's a variable along the y-axis. And we're looking for associations between those 2. And they're both categorical variables. So when you see 2 categorical variables and you want to look for an association between those 2, a natural null hypothesis is that they are independent of one another. And if they are independent, then the probability for any cell in this table, like what's the probability you end up in the unwatered status and the open habitat, if they're independent, remember statistics has this interesting definition of independence that knowing one value of a variable means nothing about the other variable. That means that the probability of both of them is just the product of the probability of each of them. So that would be defined by the probability that you're in the unwatered condition times the probability that you were in the open habitat. So that's just one of the cases of this cell. The same would hold for all possible combinations of watered versus unwatered. So there's 2 combinations there versus open and spiny and juniper. So there's 3 combinations there. So 2 times 3 gives us these 6 cells here. So we can figure out sort of an expectation for each of those cells based on the assumption of independence. So there's the raw data that Dr. Castro collected. Note we have here a null hypothesis. It's kind of specific in the sense that it's saying specifically independence, but it doesn't give us numbers. These are the data, right? These are the observed. We want to know the expected. So these are the observed values, which you might say as well, if we want to make an assumption about the expectations for each of these cells here in the data columns, based on the assumption of independence, maybe what we want to do is figure out what's the probability of being in each of these habitats and what's the probability of being in each of these conditions. So like the idea would be that the study is designed to look at open habitats. Some fraction of plants are presumably half are watered and half are unwatered, and you look at how many emerged. And so we just see the successes here, so it's hard to know exactly the probabilities, but we can generate some expected numbers by looking at the row sums and the column sums over here. So note if we sum up the rows, we get these numbers: 38 in the open habitat, 238 in the spiny habitat, 179 in the juniper habitat. If we sum all of those, we get 255 total plants that emerged. Or we could sum in the column direction, and we have 206 watered and 249 unwatered. If we sum those, we also get the same number of total plants. So you can do a double check of yourself that the column totals sum to the grand total, and that the row totals sum to the grand total. Okay, so we're interested in what the expectations are under the null. Well, if we think about it, what is the probability of being in each of these rows? And what's the probability in being in each of these columns? Well, we have some data, so we can estimate the probability of being in the rows. It's just the total number of samples in that row, 38, divided by the grand sample size, 455, or the grand sum. And that's 8.3%. In the spiny habitat, 52.3%. And in the juniper habitat, 39.3%. So here we're summing in this direction, regardless of the explanatory variable, watered versus unwatered. We're just summing to get the total numbers, and then we're converting those to probabilities. We can also do the same thing in the other direction. We can sum over all these categories. We have 249 watered plants emerged and 206 unwatered plants emerged. So 206 divided by 455 is about 45.3%. And the other probability is 54.7%. So we can get probabilities for the columns and we can get probabilities for the rows. If these are in fact independent, then we can think about what the expectations are for each of the cells. So it's kind of a weird sort of two-step process. We had the data, and from those we got the probabilities down here, and now we're going to fill in the expectations based on those probabilities in the rows and the columns. So the expectations are just the sample size times the probability of your row times the probability of your column. And so we do that for all the combinations, right? So this is the assumption of independence, that you can calculate the probability for the joint condition of being, say, open and unwatered by the probability of being in the habitat equals open times the probability that the watered equals no. And you multiply that, if you want to get in terms of expected numbers, you multiply that by the grand sample size, 455. Okay? So those are the probabilities filled in there. If we fill in the, that's just a direct translation. We're filling in the probabilities, n times those two probabilities. So we note that everything in this column has got 45.3, and everything in this column has got 54.7, and everything in this row has got 8.3%. This row has got 52.3%. So there's a lot of symmetry in this problem. We're generating these expectations assuming independence, and so there's a factor that is in common for the columns and a factor that's in common for each of the rows to give us the expectations. So it's n times the probability. There's this little weird trick where we can say, well, n times the probability of the row times the probability of the column. We could also express that as n times the probability of the row times n times the probability of the column divided by n again, right? Because these two n's would cancel off. Now, why would we do that? That just seems weird to have all these extra n's in here. We have now n squared in the numerators and an n in the denominators, and that's the same as just having an n in the numerator. The reason we do that is because the product of the sample size times the probability gives us these totals that we already have here apparent in the row totals and the column totals for this. So we can figure out the expectations for each of these cells by this formula. N times the probability of being in this row is just the observed row total. N times the probability of being in this column is just the observed column total divided by n, which is the grand total right there. So each of these cells can be figured out by the row total times the column total divided by the grand total. And you can see that played out in any one of these cells. Like the probability of being watered and juniper is the probability, is the row total associated with juniper times the row total, the column total associated with watered, divided by the grand total of 450 there. So that's just kind of a quicker method of doing this. Instead of calculating all the probabilities, you can just do the row times the column divided by the grand total. That'll give you the expectations. You can do that, and here are the expectations under the model of independence. So I just did the arithmetic here. Nothing fancy happened between these two slides, just arithmetic. Okay. So that's kind of a long-winded explanation of how we can generate some expectations under a model of independence. How do we actually test whether the data fit a model of independence for these two variables? Well, we can compare the observed minus and the expected for each of these. And so for each of the 6 categories here, we've got some comparison that we can make, and we can do observed minus expected, that quantity squared, divided by the expectation for each cell of the table. And that'll give us a chi-square test statistic, right? So here's what that looks like. Observed minus expected, quantity squared over the expectation. I just simplified what's in the parentheses just so we can see the deviations before we square them. Once again, the columns have got to sum to 0, but also the rows in terms of the deviations have got to sum to 0. So 4.8, negative 4.8, that sums to 0. Negative 0.8 and positive 0.8, that sums to 0. So you can do some double checks here that the deviations in all cases, the numerators before you do the squaring, add to 0. So that just assures that you haven't made some silly mathematical error. If you go through and square everything and divide by the expectation, you get these chi-square terms over here. The next slide we'll just simplify and focus on those numbers, not the equations of how we got them. And here they are. What we can see is there's some deviation in the open habitat, but really tiny deviations in the other habitat. So there's essentially no chi-square deviations between the watered and unwatered categories for the spiny and juniper habitat. Of course, the chi-square test statistic is the sum of all of these. We're going to sum in both directions, and we get 2.82. So that's our test statistic. Now, we want to say, is that a large number or not? Can we reject the null hypothesis that these different seedling emergence data are independent? So the hypothesis, again, is the effect of watering is independent of the habitat type, and that's what we're testing here with this. It's a pretty small chi-squared test statistic, but in order to figure out what the p-value is associated with this test, we need to know what the degrees of freedom is. And so this is similar to 8C, the last module that we recorded, in that we were estimating some parameters in order to get these expectations. So that it's the same rule that we've seen before. The degrees of freedom is the number of categories. That's 6 in this case, right? The 6 cells of data here. 2 by 3 is 6. Minus the number of parameters estimated in order to calculate the expectations. And so these are parameters estimated from the testing data that we are using. So if we think about it, we estimated the probability of being in the open habitat, and we estimated the probability of being in the spiny habitat. Once you know those two, the probability of being in the juniper habitat is just 1 minus the sum of those. So that's not really an extra parameter. That's something that we know if we know these two. So this is 2 parameters we estimated to get the probabilities for the rows. And similarly, if we know the probability of unwatered, the probability of watered is just going to be 1 minus the probability of unwatered. So there's really only one thing that we learned that we estimated from the data here, the probability of being in the unwatered category, and then we subtracted that from 1 to get the probability of being in the watered category. So what that means is we estimated 1 parameter for the columns, 2 parameters for the rows. So 6 degrees of freedom minus 2 plus 1, and then minus an additional degree of freedom, because it's k minus the parameters we estimate for the expectations minus 1. So that's 6 minus 3 minus 1. That gives us a total of 2 degrees of freedom. Okay, so in some sense, it's just the same thing we've done before. It's just this weird sort of tabular output, which gives us a certain structure, but it's the same rule that we've seen before. In order to get numbers for these expectations, back a couple slides here, we actually had to estimate these probabilities, right? And these probabilities came from 2 parameters here and 1 parameter there. And once we got those, estimated those 3 things, we could get the other one by subtraction. So we sort of fit our null expectations to the data in 3 separate ways, and that's why we lost 3 degrees of freedom here. Okay, so our chi-square test statistic was 2.82. Sorry, go back 1 slide here. Here's the chi-square test statistic. That's the sum of all the 6 values in the table. That was 2.82. Now we want to look at the table to see if that's significant. There are 2 degrees of freedom, so we look at the chi-square table on row 2, and here's the 0.05 level, significance level. The critical value there is 5.99, right? So our observed chi-square test statistic 2.83 is less than the critical value at the 0.05 level. That means our p-value is greater than 0.05, right? So we're not going to reject the hypothesis in this case. So what we can see here is that it's just a chi-square test statistic in some senses, but we just have a different structure than we've seen in the previous chapter. I didn't write out the conclusion here, but it would essentially be something along the lines of, in a sample of 455 individuals in unwatered and watered conditions in 3 different habitats, the deviations versus the expectations under the null hypothesis that watering effect does not vary across habitats, those deviations were not significantly different than what we'd expect by chance. Right? We got very close numbers. Let me go back to where we're comparing the two numbers between the observed and expected. We get some deviations in the open habitats. We had some decent chi-square terms in this row, but we're really, really close here on the other rows. And so, sure, this data doesn't look exactly like we would expect under independence. It's not perfect, but it's really close. Given sampling error and only having 455 samples, this is a really close number. How do we know that? Because when we calculate the chi-square test statistic, we get this tiny chi-square test statistic that does not come close to the critical value of 5.99. So anyway, this contingency analysis is really another form of just chi-square. It's where we get the expectations under the assumption of independence, and we're testing for dependence between variables here. There is one cute trick for figuring out what the degrees of freedom is, and so we can actually derive this. The number of categories in our combined variable, we're sort of combining the variables between, say, watered and unwatered versus the 3 habitat types that gave us a variable with 6 different flavors, but it was really composed of 2 categorical variables, one that had 2 options, watered and unwatered, and the other that had 3, open, spiny versus juniper, right? So the number of dimensions in the columns, the number of rows, that gives us the number of categories. The number of parameters we estimated for the rows, well, that was the number of rows minus 1, right? Because once we had all of them except one, we could get the other one by subtraction. The number of column parameters we estimated was the number of columns minus 1. Similarly, once we knew the proportion of unwatered, we could get the proportion of watered by subtraction. So if we figure out, use our degrees of freedom equals k minus the number of parameters estimated in order to get expectations minus 1. So there's the number of parameters, nc times nr, minus number of rows minus 1, and the number of columns minus 1. So that we sum those and subtract it, and then we subtract another one, right? So if we think about that, there's a minus 1 here and a minus 1 there. That combines to minus 2. If we distribute this negative sign, we get the product of the number of columns and the number of rows minus the number of rows minus the number of columns plus 2 minus 1. Of course, these can combine. So plus 2 minus 1 is just plus 1. So we get this expression here, and that can be simplified to the number of columns minus 1 times the number of rows minus 1. So sometimes people will say, for a contingency table analysis, the degrees of freedom is just the number of columns minus 1 times the number of rows minus 1. And that's true, but it's really just the same rule that we saw in 8c. We're thinking about the number of categories in our variable. We're subtracting how many parameters we estimated, and we're subtracting another one. So in some sense, this is just a continuation of Chapter 8, and hopefully you feel comfortable with how to do this test. If not, ask us questions in office hours or in class or email. All right, that's it for this module.